So hello everyone, welcome back to this class. Today we are going to study flight measurement of a neutral point and elevator hinge moment. So already we discussed and we have derived the expression of a neutral point. And what do you mean by neutral point? It is that CG location where the aircraft become neutrally stable. Okay. So as an engineer or designer, how will you experimentally find out the neutral point? So already we studied this equation, right? Cm equal to Cm naught Cm alpha into alpha Cm delta into delta E, and Cl equal to Cl naught plus Cl alpha into alpha and Cl delta E into delta E, right? At the trim this is 0, so from this equation you can write alpha equal to minus Cm naught Cm delta into delta E and divided by Cm alpha. Now you substitute this value in this equation, you will get Cl equal to Cl naught plus Cl alpha into, if you put alpha value, you will get this, okay, and Cl delta E into delta E, right? All right, okay. So if you simplify, you will get Cl into Cm alpha, Cl naught, Cm alpha minus Cl alpha, Cm naught minus Cl alpha, Cm delta E into delta E, and plus Cm alpha Cl delta E into delta E. All right, you take delta E term one side, okay. What you will get here? You can get Cl Cm alpha minus Cl naught Cm alpha Cl alpha Cm naught divided by what? Cm alpha Cl delta E minus Cl alpha Cm delta E, okay, and this expression is what? Delta E, okay. All right, differentiate this delta E with respect to the Cl. What you will get? I will use different color. What you will get? Dou delta E by dou Cl. So this will be the Cm alpha, this will be 0, this will be 0, and this is Cm alpha Cl delta E minus Cl alpha Cm delta E, okay. Now we know that when Cg at a neutral point, then Cm alpha will become 0. From what equation? This already we discussed. Static margin equal to xnp minus xcg, and static margin equal to minus Cm alpha divided by Cl alpha. So if Cm alpha is 0, static margin will be 0 and xnp will be xcg. So when Cm alpha is 0, dou delta E by dou Cl will be 0, okay. So that is the part we have to remember, okay, and that is the part will give you idea what we are going to do next, okay. So what you can do here, as a designer, what you can do, you can fly different Cl at different delta E with different CG position, okay. Let's say this is xcg1, this is xcg2, and this is xcg3, and this xcg1 will be greater than xcg2 and greater than xcg3, let's say if it is 0.5, this will be 0.3, this will be 0.2. Okay, so you will have a this type of graph. Okay, these are the data. Okay, let's say, okay, from this graph you can find out the what, you can find out the slope. Dou delta E dou CL. So when you find out the slope, you can put this slope here. Okay, let's say this. Okay, and you extend this line, and this is what, neutral point, and this axis you have a xcg. So finally you reach at that cg location where dou delta E by dou CL become 0. Okay, why? Because CM alpha is 0. So you can actually find out the neutral point using this flight experiment. And how will you do this different CG? You can distribute the weight. Okay, let's say if you are flying with a 6-seater, you can go with the first 2 passenger, then 4 passenger, and then 6 passenger. So you can have a different CG location you can fly. Okay, and different velocity, you have a different CL. In order to maintain that CL, you have a different delta E. So all things in your hand. Okay, that is how the neutral point is measured experimentally. Now the next topic is elevator hinge moment. So you already explained to you, there is a surface attached to the horizontal tail, that is called elevator, which is used to control the pitch of the aircraft. When it is deflected up, plane will try to go up, and deflected down, plane will try to go down by decreasing the lift and increasing the lift at the tail. Now, so if it is attached to the horizontal surface, then means some hinge line is always there, right? So you can see in this figure there is a hinge line where you have attached. Okay, now when you deflect the elevator, whether it's down and upward, there will be aerodynamic force. Okay, that force will produce the moment about this hinge line, that is called hinge moment. Okay, and let's say if you are a pilot, if you are flying, okay, so that means if you are deflecting the elevator down and you are getting the moment, this moment, and that is producing the hinge moment in a, what you can say, anti-clockwise. That means every time you need a force in order to hold this elevator at this position. Okay, so in order to zero out the hinge moment, there is a different technique. What can be this technique? So there is a different technique to do this. And one more thing, what you can do, you can use tab. When this elevator is going up, there is a negative lift, so that is producing the clockwise hinge movement. At the same time, you can deflect this tab in a downward direction. That means deflection of elevator and deflection of tab will be opposite. If it is going up, here the lift is decreases, but you deflect the tab in a downward direction to increase the lift. That means what the moment is producing the clockwise, you can produce with the anti-clockwise using this tab, and you can cancel out the hinge moment. But again there is a disadvantage. That means you will lose the effectiveness of the elevator. Okay, but this is a very effective surface to do, to zero out the hinge moment. And as a designer or engineer, how will you write the hinge moment and how it will affect your overall stability of a aircraft? So you can write hinge moment ch equal to ch naught ch alpha into alpha of the tail plus ch delta E into delta E. Okay, and you may write the tab term already as given to you, the field delta T into delta T. But as of now, since airfoil which is used to design the hinge moment elevator, okay, the airfoil which is used to design the elevator tail is symmetrical, so this term will be 0. And as of now, I am not taking an account of a tab, so this term becomes 0. So finally you may reach to this equation ch alpha tail into alpha of the tail plus ch delta into delta A. Now, if you allow to free the elevator, this moment will be 0, and this is delta alpha tail of the ch alpha of the tail. You can write ch alpha of the tail into alpha of the tail plus ch delta E, and you can write delta E free. Elevator is free. Rotate. Okay. So now from this expression, what you will get, delta E free, you will get ch alpha of the tail divided by ch delta E into alpha of the tail. So let's say air is coming, okay, and alpha is positive. This both signs ch delta E and ch alpha tail and ch delta is negative, and alpha t is positive. So you will get delta E free. That means elevator free will be upward. It will float in upward. Naturally, if the air will come, it will try to float up. Okay. So from this expression also you can see. Okay. Now, when you got this, then one more thing I want to tell you, the type of design of a hinge and all will directly decided by this derivative. So if you want to know more detail about, you want to have a more feel about the hinge, how to design the I mean to say how to place the hinge line, how will you do aerodynamically, how will you do mechanically in detail. If you put the comment, I will try to explain in detail. Okay.